This is problem number 15 in chapter 11. It reads, a mass sitting on a horizontal frictionless surface is attached to one end of a spring, the other end is fixed to a wall. 3 joules of work is required to compress the spring by 0.12 meters. If the mass is released from rest with the spring compressed, the mass experiences a maximum acceleration of 15 meters per second squared. Find A, the stiffness constant, and B, the mass. Let's take a look at the image that I've grabbed off the web. And so we can see here that if I were to take a closer look, this might be the starting position here, and this might be the final compressed position. And the distance between those 2 points is obviously important. The distance between here is the compression of the spring x. So, and since it's a maximum compression, I could call it the amplitude. That distance is given to us in the problem. As I look at number 15, that is 0.12 meters. So this distance is 0.12 meters. So some of the questions I'm answering, first they want to know what the K value is of the spring, and secondly they want to know what this mass is, this guy. So let's start with part A. This is going to be found using the work energy principles. So you might recall that from previous units, work causes a change in energy. If I take a look at the spring, we can see that the spring here initially doesn't have any stored energy because it's not compressed. Somebody applies a force here on the mass and compresses the spring, giving it 3 joules of energy. So therefore, the 3 joules of work that are done are equal to the energy possessed by the spring, which is equal to the elastic potential energy held by the spring, which is going to be equal to 1/2 K times A squared, where A is that amplitude, or that displacement in the horizontal direction, 0.12. Solving for K, I'm going to multiply both sides by 2, and really I'm just using this guy, the work, and this guy, 1/2 Ka squared. So when I end up multiplying both sides by 2, I get 2 times the work divided by A squared is equal to K, my constant of elasticity. So that's going to be 2 times 3 joules of work, and I'm going to divide that by the amplitude, 0.12 meters, and I got to remember to square that, is going to be equal to the constant of elasticity. When I run that through my calculator, I get 416.7 newtons per meter, being the units for that spring stiffness constant. Truncating for significance, I'll round that to 420 newtons per meter. And so therefore, my answer for part A is 420 newtons per meter, or 4.2 times 10 to the second newtons per meter. Part B asks me to figure out what the mass is, and part B will be solved by recognizing that when I am here at this position, I'm going to call this the starting position, position 1, and the maximum compression, position 2. When I am at position 2, I'll recognize that there is a net force caused by the spring, and that net force is the spring force. It's the restoring force on the spring. And that's equal to mass times acceleration, because net force is equal to mass times acceleration, and it's also equal to negative kx. So I put a lot here. This probably isn't the best way to present the material. I could have kind of presented it individually here. So let's go ahead and do that. Of course, F net equals ma. That's Newton's second law. And we can also say that the restoring force of the spring is equal to negative kx. So I'm looking for the mass when the acceleration is known. So I know the acceleration, I know the displacement x, that's 0.12 meters, and I know k. So I'm going to solve this problem by setting those two forces equal to each other because they are one and the same. I get F net equals the spring force, or I resolve it to just ma is equal to negative kx. Solving for m, I get negative kx divided by a, and I get negative k. Now my displacement is to the left, so that x, or a if I decide to use that variable in place of x because it's a maximum value, is going to be 0.12 meters to the left, negative 0.12 meters. And I'm going to divide that by my maximum acceleration, which was again given to me in the problem. It's 15 meters per second per second. Now I'm going to take this value of k that I figured out earlier in the problem, actually this one right here, 416.7, and plug that in here. and then I'm going to turn the crank on the calculator, multiplying that by 0.12 meters and dividing by 15 meters per second, and I'll get an answer of 3.33 kilograms. Now, I want to deal with some significance, so I'm going to go ahead and call that mass 3.3 kilograms. 2 sig figs, and call it a day.